Alright guys, here we go with systems of equations, or actually this is system of inequalities, and the way to solve a system of inequality is through graphing. And it's our only method for solving a system of inequalities.
Are we rolling?
Yes, we're rolling.
Objectives. I can solve systems of inequalities by graphing, and I can solve real-world problems using systems of inequalities.
Alright, here's our vocabulary. Here's what a system of inequalities is, and here's an example of what it may look like. So if you need to, pause the video and write this down. Alright, so how can you solve a system of inequalities? So to solve a system of inequalities, you have to find all the ordered pairs that satisfy all of the inequalities. And to do this, you graph it on the coordinate plane. And the solution set is the shaded area, the areas of the graph, the shaded area of the graphs, where they overlap, where they intersect. What that means is your shaded area on your graph, as always, is the area where any ordered pairs that you pick there are going to satisfy all the inequalities. Your shaded areas is where your solutions are. Alright, so basically, here are our steps for solving, and for solving an inequality. We do the same thing we did when we solved just one linear inequality. We're going to do it when we have a system of linear inequalities. We're going to follow these same 5 steps right here. What we're going to do is we're going to follow those 5 steps for the first inequality. Then we're going to follow those 5 steps for the second inequality. And what we're going to do is we're going to shade in the area that is shaded by both or more of those inequalities. So let's go ahead and give it a shot and try one. Alright, so here's our first example. We're going to work on each inequality one at a time. I'm going to color code my first one blue, and I'm going to follow my 5 steps. So first of all, line type. No line underneath it for the or equal to, so that means it's a dashed line and an open dot. So now I need to put it in slope-intercept form. My slope-intercept form is y equals mx plus b. Basically, I just need my y by itself, and look, it's over here by itself. So all I need to do is graph, because it's already in slope-intercept form, which is my blueprint for a graph. So first of all, my starting point is my y-intercept. My y-intercept is the number that does not have the variable x attached to it, so it's 1. So I have an open dot at 1. Then I'm going to use my slope. My slope is the number attached to x. I have a negative in front of there. There's no number, but I know that there's no number. It's a 1. And I need my rise over my run. So I'm going to take that and I'm going to put it over 1, because negative 1 over 1 is 1. So what that means is I fall down 1 and I go over 1. I fall down 1 and I go over 1. So this is basically a sketch of what my line looks like, and it is a dashed line with open dots. Now I need to choose a test point. So I'm going to choose 0, 0, because remember, my test point can't be on the line, and 0, 0 isn't on the line. So I'm going to substitute 0 in for my y in my equation, and 0 in for my x. So I have 0 is less than 1. Is 0 less than 1? That's true. Yes, it is. It is smaller. So that means I shade on the side of the line that has that point. And remember, what that shaded area means is any ordered pair I choose in this shaded area will satisfy that inequality. And because I did a dashed line, it means any ordered pair on the dashed line will not satisfy the inequality. Alright, so now I'm going to form the same 5 steps with the second inequality. I'm going to color code it red. So first of all, line underneath means solid line, closed dot. Is in the slope-intercept form? Yes, it is, because y is by itself, so I can go straight to my graphing. My starting point is 1, 2, 3. That's my y-intercept, the number without x. And my slope is 2. and get my rise over my run, I do 2 over 1, so that means I go up 2 and over 1. And so my line for this one is going to look a little bit like this. Alright, now I need to choose a test point, and I'm going to choose 0, 0 again because it's not on the line, and 0, 0 a lot of times, if you can substitute that in, that's the easiest substitution to make. So I plug in 0 for y, and 0 for x, and 0 is less than or equal to 3. Is 0 less than or equal to 3? Yes, it is. So that is also true. So that means I shade, oops, not like that. Alright, I shade on this side of my line. Alright, now, because I'm concerned with where these two lines intersect here, I only want the area that's shaded blue and red, not just the blue and not just the red. So I'm going to erase. This right here is my red area, and this right here is my blue area. So really, and I'll color code it purple, so hopefully you can see it a little bit better. It is this area right here. This is my shaded area. This is the solutions that satisfies both inequalities, what I'm coloring purple. That's the only area I shade, is the one shaded by my solutions for both inequalities. So it's this area right here. Alright guys, here's example 2. You're going to follow the same steps. You'll notice that both of these here are going to be open and dashed because there is no equal to sign. And you've got to put them in slope-intercept form. So I'm going to start you out by putting them both in slope-intercept form, and let's see if you can take it from there. So first of all, I'm going to do my first one here in blue. I need y by itself, so I've got to move the x over. So now I have negative y is less than negative x minus 1. Then I've got to get rid of the negative in front of the y. And remember, with an inequality, if you multiply or divide all the way through by a negative sign, it flips the direction of your inequality. So here is my equation for the first one. Now I'm going to, in red, do my second one. Same thing here. I've got to move the x over. So I get negative y is greater than negative x plus 3. And I've got to get rid of that negative again. Alright, and when I do that, remember I've got to flip my inequality. And I get x minus 3. Alright, so here is my first one and my second one. Let's see if you can come up with the graphs. So let's pause the video, see what you come up with, and then restart and check your answer with mine. Alright, so here's the graphs I get when I graph my two inequalities. If you'll notice here that the red and the blue do not overlap. There is no overlapping or intersecting shaded area, so what that means is this one has no solution. And I misspelled solution. So it has no solution. There is no overlapping shaded area on this one. Alright, here's a word problem we're going to do to graph a system of inequalities. So here's our situation. We have the middle 50% of first-year students, FSU, score between 520 and 620 inclusive. Inclusive means that they can score 520 and they can score 620 on the verbal portion of the SAT. And between 530 and 630 inclusive on the math portion. Graph the scores that the students will need to be in the middle 50% of FSU freshmen. Well, steps for solving a problem when we have an application problem or a word problem is, first we're going to have to define the variables. So we're going to just have to name them like our x and our y. Then we're going to write inequalities that represent the situation. Then we follow all of our steps to solve a system of inequalities. Alright, so here is what we have for the solution to this problem. We let V be the math score, V be the verbal score, M be the math. Our verbal scores are going to be in between 520 and 620, and because it says inclusive, that means the or equal to, so we put the line underneath our inequalities. And the same thing with the math, it's between 530 and 630 inclusive, so we put the lines underneath to include that. We actually, on this one, don't have to be solved. There's no solving necessary on these. All we have to do is graph and figure out what the overlapping shaded area is. So here's our graph here. I'm going to make the x-axis my verbal and my y-axis the math. And let me see, it was from 520 to 620 on the verbal. So I am going to, let's see, I'm going to go 200, 400, 600, and I'll go 800. I'll do the same thing. You're going to have to figure out how to scale these yourself. 400, 600, and 800. And I think the verbal on this one was from, Sorry, I forgot my scores there for a second. So let's see. The verbal, they scored from like 520. So that would be, we'll make that blue. 520 should be around here. From 520 to 620. So that would be this area right here. And then on my math scores, it would be from about 530 to 630. I did solid lines because it says it's inclusive, and my shaded area would be over here. So what that means is that middle 50% would actually be right in here, my overlapping shaded area. So this is my only shaded area. I would basically, this wouldn't be shaded, this wouldn't be shaded. I have to have just the intersection, that overlapping part. So my only shaded area would be this little purple section here. All right, here's another application problem. So it says, to ensure a growing season of sufficient length, Mr. Grant has at most 16 days left to plant his corn and soybean crops. He can plant corn at a rate of 250 acres per day and soybeans at a rate of 200 acres per day. He has at most 3,500 acres available. How many acres of each type can he plant? All right, well, the first thing we've got to do is define our variables. So what we're going to do is we're going to let x be his corn, how many days or how much time he can spend on corn, and y be his soy. All right, and that's supposed to be an O. All right, so first of all, he can never plant a negative amount of corn, so his amount of corn he plants has to be greater than or equal to 0, and the amount of soy has to be greater than or equal to 0. Normally in real-world situations, we only deal with positive numbers. All right, next of all, when it says that the amount of time he has to spend planting corn plus the amount planting soy can be at most 16 days. So it has to be less than or equal to 16. He also says he has a rate of 250 per day for the corn, plus a rate of 200 per day for the soy, and he has at most the 3,500 acres to plant. So 250 acres for corn, 200 for soy, and at most 3,500. So there's all of our equations. All right, next we're going to take all that information and graph it. First of all, I said my x-axis, that was my corn, and my y-axis, that was my soy. I had to, when I said x is greater than or equal to 0 and y is greater than or equal to 0, that meant I was just using my positive x-axis and my positive y-axis, that first quadrant. And with my two equations, I will use them as equations. X plus y equals 16 and 250x plus 200y equals 3,500. basically the easiest way to get these is to use your X and Y intercept. So I'm going to go, let's see, 5, 10, 15, 20, and 5, 10, 15, 20. I already have my intercepts. I've already found these, so you should do that first before you sort of scale this. That's why I know to scale this by 5 is because my x-intercept here is going to be 16 for this one. And we'll do that in red so it's easier to see. And my y-intercept is going to be 16. So for this line here, less than or equal to, if I plug in that 0, 0 for it, I know that makes it true. So here is my line if I connect my x and y intercept. And my shaded area is going to be down here. Alright, for my next one, I've already found my x-intercept and my y-intercept. My x-intercept for this one is 14 and my y-intercept is 17.5. So I'm going to plot those points. Let's see, 14 and 17.5, and I connect those. And if I plug in a test point, 0, 0, 0, 0, let's see, 0 is less than or equal to 3,500. So for my blue one, I shade underneath here. So what that means is my overlapping shaded area is going to be what's underneath both the red and the blue line. So my overlapping shaded area, and that's where my answers come from. So my answer is the graph, and it's just going to be this area underneath both lines. It's not what's just underneath the blue. It's not what's just underneath the red. It's the area that's underneath the blue and red. So any of my solutions for this can come from any of this shaded area. And that also includes, since it had the or equal to part here and the or equal part here too, it can come from this point here on the y-axis and this point here on the x-axis and any point in the shaded area. Alright, here's one last application problem. It says Natasha walks and jogs for at least 3 miles every day. She walks 4 miles per hour and jogs 8 miles per hour. She exercises at least half an hour. It wants you to graph and list 3 possible solutions. So, first of all, I've given your inequalities for you, and remember, it's always going to be positive, real world situation. She's either going to walk 0 hours a day, or she's going to do it more than 0, and she's going to do the run, the jog at least, none or some. Okay, here's my other 2 equations. So find your x and y intercepts and graph it. So give that a shot, and then when you're done, restart the video and let's see if we found the same shaded area. Alright, so once again, and really in real world applications, finding an x and y intercept, and that's why we did it before, is the easiest way because the numbers are usually large. So I found the x and y intercept of x plus y is greater than or equal to 30, and I found the x and y intercept of the other equation. And from that, I use my test point, my overlapping shaded area, and this purple here is my overlapping shaded area between those 2 inequalities. So really you can pick any 3 points in this shaded area and they will satisfy the situation. So that's it for solving systems of inequalities.